So let us look at linear convolution. And I would like to introduce you to the matrix notation so that you feel comfortable, because matrix notation is the one that gives us a very compact mathematical representation of what the operation is. So let us say that we have two sequences, x1 of n, which is the two sequences, the same one which we did circular convolution. One of them is of length 4, 1, 2, 0, 1. Okay, and the second sequence x2 of n, if you remember what the sequences that we worked on, 1, 2, 0, 1 and 2, 2, 1, 1. Okay, so that's what we are going to be looking at. So this is 2, 2, 1, 1. Now the first thing I want you to do is to do linear convolution. Linear convolution. I'm sure you have studied that in signals and systems. So what we are saying is, convolve this sequence 1, 2, 0, 1 sequence. Convolution is usually indicated by an asterisk sign, linear convolution, and with the sequence 2, 2, 1, 1. And of course, you will time reverse one of them and then you will multiply. But how do you represent this in a matrix form? Okay, the very useful way to represent it in terms of a matrix form. So let us say that we have the x1 and you're going to time reverse x2. Okay, so x1 we write down as a vector 1, 2, 0, 1. That is the vector x1. Okay, this is x1. Now what we're going to do is we're going to write down the representation which comes from the convolution. So time reversal, so which means that 0th position will be there. The other samples will come to the left. So 2, 2, 1, 1, time reversal. Okay, and let's assume that in this position there are all zeros, there are zeros. So what we have done is we have time reversed the sequence, and this corresponds to index 0. Okay, this corresponds to index 0. So now we can calculate what is the value of the output when you look at the convolution or the first sample of the convolution. So you multiply these two together and say that the first sample is going to be equal to 2. Second sample, how do? You shift right. So then it becomes 2, 2, 0, 0. Then the sample value, if you calculate, this will come out to be equal to 6. Okay, next one, shift one right to the one more time, 1, 2, 2, 0. You get a value of 5. Then shift one more time, 1, 1, 2, 2, you get a value equal to 5 again. Now what happens? You keep shifting. Now it goes outside the window of the convolution. So at this point, zeros start to appear again. You have 1, 1, 2. That is the next computation. If you work that out, that will come out to be 4. Then one more step, 0, 0, 1, 1. That will give you a value equal to 1, and then finally you get the last equation 0, 0, 0, 1, that also gives a value equal to 1. So notice that we convolved to length 4, n equal to 4, n equal to 4. The output, if we call that as y of n, has got length n equal to 7. You can calculate and see that there are 7 samples, and this is equal to 2, 6, 5, 5, 4, 1, 1. Okay, let's indicate the origins for all of them. This is the origin, this is the origin, this is the origin, and length equal to 7. So this is linear convolution. Okay, I hope you are completely comfortable with the aspect of what we have done. All right. Now, what does, can we represent circular convolution also in a compact matrix form? The answer is yes. So we will do the same thing, but now remember the two vectors are of length 4. So what we're going to do is we're going to do circular or periodic convolution. Periodic convolution, and it is going to be represented by x1 of n a 4-point circular convolution of x2 of it, with x2 of it. Okay. Now, what we are going to show is just how to capture that. This 4-point circular convolution will produce for us a sequence x3 of n, which is also of length 4. Now, how do we get that 4-point convolution? So let us write it down. Circular convolution. Okay, the vector x1 exactly like before, 1, 2, 0, 1. Remember, we started out saying the first vector of the first sample of the second sequence, which is time reversed, 2, 2, 1, 1. Okay. Now, previously what did we do? We inserted zeros in the rest of the row. Now, what we are going to do is something very interesting. Okay, we are going to take this and say that, okay, it's going to come here. So, that means 1, 1, 2 are going to come here. Okay. So, then what happens? It's as though this first sequence was actually periodic sequence. The segment from the next period has already come in. So, basically that's what is captured here. So, now if you multiply and see, so the important thing is what did we get as the result last time when we did the computation? The x3 tilde of n was a periodic sequence with this period 6, 7, 6, 5. That was the output that we got. Now, if you look at this computation and carry it out, verify that the first sample comes out to be 6. Okay. Now, what happens to the second row? Exactly what we did last time. Shift everything to the right and make sure that new samples are coming in from the left. So, what happens here? So, we say 2, 2 and then 1, 1. Okay, multiply, you will verify that this comes out to be equal to 7. One more step, move it around, 1, 2, 2, 1. 1. What is the output? This is equal to 6. And the final step, you have 1, 1, 2, 2. This will give you a value equal to 5. Okay, value equal to 5. And this is exactly what we got previously, 6, 7, 6, 5. Okay. So, you can verify 6, 7, 6, 5 is the output of circular convolution. So, this is circular convolution. This is linear convolution. Okay. Very, very, very important results. How to put it in the form of a matrix operation. Okay, now comes a very interesting observation, which I hope you will try out and appreciate what is happening. Okay, now I'm going to create a modified sequence x1 tilde of n. Okay, so this is going to be the original sequence 1, 2, 0, 1, but I'm going to append 3 additional zeros. Okay, so total length n equal to 7. Okay, we're just using we're looking at one period, so there's no need to represent it as a periodic signal. Similarly, I'm going to write down the second sequence x2 of n as the sequence that we had before 2, 2, 1, 1 appended with 3 zeros. Okay, this is also n equal to 7. Okay. Now, if I were to tell you, please write down the matrix form of the circular convolution for these two sequences. Follow exactly the same procedure. Let us say that x1 will not be time reverse. So, you will basically have the sequence written as a vector. The vector will be 1, 2, 0, 1, 0, 0, 0. Okay. And what about this matrix? It will be a matrix which is 7 by 7, and the first coefficient is going to be 2, and because of the time reversal you have 2, 2, 1, 1, 0, 0, 0. Okay, now repeat that, 0, 0, 0, 1, 1, 2. Okay, tell me what the output is. You can look at the calculation and then tell me that the output will be equal to 2. Okay. Now shift it one more time, one step. So it becomes, let me use a different color here so that we can visualize what is happening. Okay. So the next step, it will be 2, 2, then it will be 0, 0, 0, 1, 1. Okay, then it will be, let's quickly write down the rest. This will be 1, 2, 2, 1, 1, 2, 2. Then it will be 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2. Okay, and whatever is left out will, this will be 0, 0, 0, 1. This will be 0, 0, 0. 0, 0, and a 0 now comes from the next segment. This will be 0, 0, and then finally 0, 0, 0. This is how the matrix will look like for the circular convolution. Very important. Now please go ahead and do this computation. What you will find is that this will be 2, 6, 5, 5, 4, 1, 1. What did we do? We did the circular convolution. X1 of n 7-point circular convolution or periodic convolution with X2 of n. This is what we did. Okay. Now let's go back and look at the sequence that we obtained for the linear convolution that we did. Okay. 2, 6, 5, 5, 4, 1, 1. What did we get with the periodic convolution? 2, 6, 5, 5, 4, 1, 1. Okay, what is the observation? The observation is that the 7-point output of a linear convolution of two sequences of length 4, convolution of x1 of n and x2 of n. This produces identical results to the 7-point circular convolution of x1 prime of n and x2 prime of n. Okay, and what is this? This is nothing but x1 of n with 3 zeros appended. Okay, a very important observation. By appending the correct number of zeros, we can actually get the same result as linear convolution. Okay, let me repeat that. By appending zeros and doing circular convolution, we can get the same output as linear convolution. Now, why is this an important result? So, here is a small box that I want you to keep in mind always. Okay, LTI systems, the input-output relationship is y of n equal to x of n convolved with h of n, right? Now, this is linear convolution. Okay. Now, if you are going to use the properties of the discrete Fourier series, then we can say that we will look at the periodic versions of these signals. So basically, what we are saying is we will look at the convolution that will happen. So if, let us say, x tilde of n, periodic sequence has x tilde of k, h tilde of n has got a discrete Fourier series representation, which is given by h tilde of k. Okay. Now, I can easily compute what x tilde of k and h tilde of k is multiplication, and then I can compute what is the inverse discrete Fourier series or basically the synthesis equation, and this will give me what y of, so if this is y tilde of k, then from here I can compute y tilde of n. Okay, so rather than do the convolution in the time domain, I would prefer to do it in the frequency domain. Now the only problem is when you multiply the two DFS coefficients, what you get is circular convolution or periodic convolution. So if you are able to pad sufficient number of zeros, then what we get is the linear convolution. So we can use the discrete discrete Fourier series representation or the discrete Fourier transform representation for linear convolution, because that is what we are interested in. The transform itself inherently produces circular convolution or periodic convolution, but with sufficient number of zeros getting added, we can get the desired result. So what are some of the key things that we have covered? First is how to do time reversal. Then how to represent the periodic convolution. You can look at it in terms of two circles or a circle where you have the outer circle and inner circle, or you can think of it in terms of a matrix representation. So you can see how linear convolution is represented as a matrix equation, how circular convolution is represented or periodic convolution is represented as a matrix equation. So the difference is that in the context of circular convolution, the matrix is 4 cross 4. The dimension of the matrix is 4 cross 4, and the other vector is 4 cross 1, and the output will also be 4 cross 1. So that is the periodic convolution. Two segments which are both having the same period. When I do the circular convolution, I produce another periodic sequence. Now the same thing, if I append enough sufficient number of zeros, I am still doing periodic convolution. However, the output looks the same as the linear convolution. So that is an important result which we will leverage, and that we will try to utilize in multiple ways.